Okay, good morning. So we will move on to the 8th module. So we can see that we analyze the enclosure fires in the last module, which was basically fire within some confined space and the characteristics of them. Now we will go to some introduction to dust ignition, then dust explosion. These are special cases basically, which can occur in industries handling dust and all. Then we will also see something about forest fires. Dust also called powders. They are basically micron size particles. Micron size means it should be actually less than 500 microns, 0.5 mm. So if the particles are less than 0.5 mm, then the group of these particles can be called a dust. So it can be organic dust like powders, then it can be coal dust, which can be uh, due to, if you go to a coal mine, you will see a lot of coal dust, etc. So many materials, see for example, if you take a material like an organic material which is in bulk form, you try to ignite this, say organic material, you try to ignite it, it may not ignite, it is non-flammable. But if you make it powder, that is particles having size of average size, you can say less than 500 microns, then it becomes highly flammable. This dust which are dispersed in air becomes flammable, it can burn. Even metal dust, no, iron powder, etc., copper powder, they can burn in air when they are actually, when they are dispersed in air to form a cloud of fine particles, they can burn. Iron, you cannot burn it very easily. Say if you take an iron rod, you can't burn it, but iron powder, which are very micron size powder, which is dispersed in air, if the air temperature is higher or it is ignition source, it can burn. That means we have to be very careful when we have industries which manufacture, transport, process and use powders or dusts. Powders are also called dusts because they can run into dust ignition. Then when there is a dust ignition, there can be flame spread over the dust dispersed in air, that is called dust deflagration, flame spread at subsonic speed, dust deflagration. Or if this dust is dispersed in air in an enclosure, then it can also cause dust explosion. You can see that means there are lot of safety protocols needed to handle these dusts, because it will lead to natural hazard where personal and equipment losses can occur. Now, fire caused by micron size particles results in extensive damage, injury, loss of life, where, for example, in coal mines, wood, paper, chemical processing industries, food processing industries, grain processing industries, and pharma, where medicines are made. Medicines are basically made using a lot of chemicals which are in powder form. So, lot of safety protocols. So, to understand these fire caused in micron size particles, we have to understand how it can be ignited, how the particles burn, etc. So, many organic dusts, say for example, in the food processing industry where you process wheat, rice, etc., or wood processing industries, these are organic dusts, even sugar, they are very highly flammable, especially when they are in the air, dispersed in the air as a cloud of fine particles. Okay, so that means that, so wheat itself, for example, a wheat without, so for example, a whole wheat cannot be ignited so easily. But if you have a, or maybe you have non unground wheat or rice, etc., you cannot ignite it. But if it is in powder form, it will be ignited very fast. Similarly, wood, you have seen that wood ignition is very difficult, but wood powder or wood dust will ignite at a faster rate. Now, let us first go and discuss about dust layer ignition. Because when you have industry or facility which handle dust, in coal mines, dust is formed when you mine the coal, dust is automatically formed, coal dust is automatically formed. This dust accumulate over surfaces which can be hot. Now, a flammable dust deposited over the hot surfaces is a common industrial hazard. Okay, especially when the dusts are less than 400 microns. So you have a hot surface and some dust is accumulated over, dust layer is accumulated over this of a particular thickness. Okay, so I say this is the thickness of the dust layer. This is having a temperature of TH, hot surface. Now, this can ignite this dust. Once dust is ignited, this can cause ignition of further commodities and so on. And when the dust is ignited, it can also be fugitive, that it can also fly over and basically go and cause ignition. Basically, dust is fugitive, so that is, it can easily fly over places and accumulate over surfaces. So now, if it accumulates over, say, machinery, switchboards, electrical conduits, etc., where there will be hotspots, then you can have the danger of the dust layer getting ignited. The dust layer will get ignited only when there is sufficient thickness and sufficient temperature of the surface. Okay, so we have to understand at what condition a particular dust will get ignited. So that is, see, for a given dust, say for example coal dust of 1 inch thickness can be ignited when the surface temperature is about 100 or 200 degrees centigrade, like that. So we have to understand the minimum threshold temperature TH of the hot surface which can cause an ignition. And this ignition is called spontaneous ignition, like auto ignition, but it's a spontaneous ignition, where now the dust layer temperature will exceed the value of the, this is dust layer temperature, will exceed the value of TH after some time. So that is called dust ignition, which is spontaneous in nature. This increase in temperature now can be an ignition site for combustibles which are present nearby. Maybe some pyrolysis gases also will be there, that can be auto ignited due to this increase in temperature. So that means dust ignition can cause further fire hazards. So spontaneous ignition of dust occurs when enough energy is supplied to trigger an exothermic chemical reaction that can lead to sudden rise in temperature. So we have several forms of dust which are handled by several industries. So we have to categorize the dust based upon the conditions where it can ignite, that is, what thickness of accumulation will lead to ignition, what should be the threshold temperature, etc. So that means we need to categorize the dust or characterize the dust and see what is the threshold temperature, thickness, etc., which can cause spontaneous ignition. Now, one more thing is energy is supplied through radiation to the dust. That is also possible, because if the dust is deposited over a confinement or any enclosure where there is a heat source and radiatively this can heat the dust, then similarly, for example, there may be some surrounding temperature which are high enough to cause this ignition, or maybe the system is deposited over a surface which is at a higher temperature. So something should happen which will cause some energy supplied to the dust which can trigger the exothermic reaction causing a increase in temperature. It is not a flaming combustion. Okay, so dust ignition will not lead to a flaming combustion generally. But as you see in the handling industries, these three causes, main cause will be the hot surface where the deposition of dust can cause to or lead to dust ignition. So since many industries have seen such dust ignitions due to the handling methodology and depositions of dust over hot spots, there should be some standards to categorize the dust. So since this is a safety issue, to address this, some tests which are standard based tests are conducted to determine the minimum temperature which is going to cause the spontaneous ignition of the dust layer, but this dust layer should have a certain thickness. So maybe you vary the thickness and see at what minimum temperature of the surface the spontaneous ignition occurs. Now, how to do this? There is a standard test procedure. You have a ring of standard dimensions. A ring of standard dimensions. So the front view will be like this, and you deposit the dust over this, and this is kept in a hot plate. This is ring, and dust is deposited over this ring basically, and the hot plate temperature can be controlled. Surface temperature can be controlled. Now I put a thermocouple here to find the dust temperature and see whether for this condition of dust layer thickness, whatever be it is, T, and this TH, TD exceeds TH or not, causing spontaneous ignition. Okay. Basically, we need a condition where the dust temperature should be greater than TH by above 50 degrees centigrade. So this is the standard test procedure. Based upon some ASTM or European standards. A typical ignition test as per ASTM E2021 is shown here. So this is the hot plate. So hot plate facility where this is surface which will become hot, and this is a metal ring over which the dust is deposited. So dust is deposited in the ring, and you can see that there is a thermocouple which is put in the center to measure the temperature of the dust. So schematically you can see that hot metal plate. So this is at a given temperature. By controlling the power supply, input power supply based upon what is the temperature of the surface, I can precisely control the temperature of the surface. By varying the power supply to the circuit, I can control the T. That is, I can maintain the hot plate at a given temperature TH. And this deposition, this is dust layer, and the thermocouple is kept in the dust layer, and this dust layer has a certain thickness T. Now I know TH, I know the thermocouple reading. When the dust temperature, so this will read TD. When dust temperature exceeds the hot plate temperature, then we can say that the dust has ignited. Okay, or the dust layer will deform. You can see the deforming crack formation. So visible signs are deformation, crack development, etc. can occur. So, by viewing that or by measuring the temperature, say always you may not measure the temperature. So, just by visible signs you can say that ignition has occurred or not. But if the temperature TH is below the threshold temperature, it will not cause any. So, there will be some heating of the display, but it will not cause spontaneous ignition. The spontaneous ignition will be caused only when for the given thickness of the dust layer there is appropriate threshold temperature of the metal plate TH that is given. So, now the dust layer ignition now is conducted in considering Pittsburgh coal dust as the fuel. Now, you can see that this is the temperature which is kept in the thermocouple, measured by thermocouple, kept within the dust layer, and the plate temperature, this is the hot plate temperature TP. Now we can see that when the hot plate temperature is kept at 180 degrees centigrade, the temperature of the dust layer, this actually is it, T is the dust temperature in the dust layer. So that increases from the ambient condition, increases, but it increases only to about 100 degrees and remains constant after that. That means there is a 80 Kelvin difference. There is no increase in further increase. There is some heat transfer, but it is not able to ignite the dust layer. You can see that even after about 200 or 300 minutes, you can see about 250 minutes, there is no sign of increase in temperature beyond a value of about 100 degrees centigrade, where the plate is kept at 180 degrees centigrade. So, for the given thickness, this is 1 inch thick or 2 inch thick or 1 or 2 inch, okay. So, 1 or 2 inch thick dust layer, okay. So, basically for a given thickness there is a given plate temperature Tp which can cause ignition. So, what is ignition? There are two things. First one is, if you see this ignited, this is coal dust where ignition criteria is positive. That means you can see the crack formation, and the layer which was very uniform and smooth layer, distorted layer has come, okay, distorted layer. So, visible signs. Plus, this has happened when Tp is 190 degrees centigrade. So, first I conduct the experiment in 180, I found that there is no increase in temperature. So, no ignition case. 180 Tp for this thickness is no ignition case. Now, I increase the temperature to 190 degrees centigrade plate temperature. Now, I see this brown line increases, but the rate of increase increases nicely, and now it goes past the plate temperature and exceeds that plate temperature. This point around 3 hours, it has exceeded the temperature of the plate by 50 degrees. So, this is the criteria for ignition. Then this is the, then after that it rapidly increases, you can see rapidly increases temperature. That is, here exothermic reaction as onset in the dust layer, and you can see that the dust layer has distorted itself. Cracks are formed. Cracks have been formed. So, this is the standard test where I keep a given dust layer of some thickness, 1 inch, 2 inch, half an inch, whatever, and for the particular case I control my hot plate temperature Tp at a given value, set that at a given value, and see, monitor the temperature of the dust layer T as a function of time and see whether it exceeds the temperature by 50 degrees centigrade. So, in this particular case for Pittsburgh coal, these are experiments conducted in WPI, Worcester Polytechnic Institute, Massachusetts and in near the Boston. So here you can see that the temperature increases and settles when the plate temperature is 180 degrees. There is no visible sign also. So that means the layer is uniform, not at all distorted, no crack is seen. But when a slight increase, 180 to 190, if you increase, then you can see that there's a rapid increase in the dust layer temperature. Also, the visible signs, distorted layers, crack formation, etc. are seen. So some fumes also can come out of this. Okay. So basically, for a particular fuel or dust, fuel dust, I will say, fuel dust, thickness, for a particular thickness, there is a given plate temperature, I will say critical, where ignition can occur. So that is what we need to monitor. When this temperature is set to the hot plate, that dust layer temperature will be, okay, Tp plus 50 degrees centigrade. When this condition is reached, then ignition is said to occur, apart from the visible signs. Now what happens is, when a layer of dust is in contact with the surface having a critical temperature, Tp critical, or a critical heat flux, what you can say, that is important from critical, it reaches the ignition temperature, which is called self ignition or spontaneous ignition temperature. Higher heat flux results in lower time to ignition. Yeah, so that means, see, we have varied the temperature from 180, seeing no increase in temperature, clearly no ignition case. When I make it say 185, it may not increase the temperature like this, it may settle at a slightly higher temperature. But 190 actually has ignited it. But if I set the temperature to 210 or 250 etc. degrees centigrade, then higher heat flux results, that will cause lower time. That the time to give the ignition condition to the layer will be shorter. Similarly, particle size in the layer affects the time to ignition. Okay, now in these cases, this layer is of a given size, average particle size can be say 25 microns, 25 microns particles. Now if you increase the size, so 50 microns, 100 microns, etc., then also there will be an effect on the time for ignition, the time it takes to ignite. So the temperature of the surface, particle size, etc. will also cause. Now, if the previous example, if you take coal dust is used, which is a charring material, because the coal, once the volatiles are released, then char is formed, fixed carbon plus some ash, whichever is there. This fixed carbon, which is graphite, can attract oxygen from the ambient and can, when it is hot enough, this char, the fixed carbon, when it is hot enough, that is around 850 degrees centigrade, etc., if it is heated to that level, then what happens is it can react with oxygen, forming an exothermic surface reaction. Now, once this surface reaction occurs, this can propagate down. Propagation of the surface reaction through the combustible dust layer or any charring porous material, that is the smouldering. We already seen this. Okay, now penetration occurs like in a cigarette flame, correct? It is only not a flaming combustion. Smouldering is not a flaming combustion. It will just give a red hot zone. Like this, the red hot zone propagates down. For this, there should be some porosity. There should be some oxygen entrainment or oxygen transport. So these two are important. So If the porosity is very less, then oxygen cannot enter into the layer. That means smoldering cannot occur. But the cracks which are formed after the spontaneous ignition can allow for oxygen transport. So smoldering can occur due to that. The smoldering is not a flaming combustion, it's a low temperature, gradual, slow combustion, and here it is no visible flame will be seen because there is no gas phase reaction, it's only surface reactions. Okay, now the smoldering can occur before and after the flaming condition. That means a spontaneous ignition can lead to smoldering. The smoldering can cause flaming combustion later. So that means the dust, spontaneous ignition of dust is actually dangerous because of the fact that it may trigger flaming combustion. Now, something more about smoldering basically is there is a porous fuel. Okay, air is coming from the right to left. This is the residue, maybe a ash residue, because this may be a porous fuel like charring material. Now, there are basically three zones: a residue zone and the oxidation zone, where basically C plus O2 reaction take place. This is solid, and there is a pyrolysis zone. This slowly heats up a material which is there, and this smoldering front, this is called smoldering front, this propagates consuming the porous fuel. So this is the schematic of the smoldering process, and here the peak temperature is in the range of 450 to 700 degrees centigrade for say biomass fuels. For anthracite coal, bituminous, subbituminous coals, etc., high rank coals which has good amount of carbon, solid carbon, then the temperature can exceed 1000 degrees centigrade. The spread rates, I cannot say flame spread, it is called a smoldering spread rate, are also much lower. The rate at which a smolder zone propagates is much lower than a premixed flame propagation. Obviously, because this pyrolysis zone appears next to the flaming zone or the smoldering zone, and this needs some time for pyrolysis, and that is the rate controlling. So, time for pyrolysis, Tp, time for pyrolysis is rate controlling. Okay. The heat release rate per unit area flux can be small, 10 kilowatt per meter square to 30 kilowatt meter square. Okay, in a flaming combustion it makes it 50 kilowatts meter square easily. Then what are the factors affecting the smoldering process is basically two: oxygen supply, how the, because this is residue, this may give resistance to the airflow. Okay, that is one of the thing. Then heat transfer. If there is a heat loss, the heat lost out of the smoldering layer, then what it gives to the parent material here, if that is exceeding, then the heat transfer, these are the two things. It should, the smoldering layer should heat the subsequent parent fuel layer, plus it also should attract oxygen. So preheating, drying, pyrolysis and oxidation, these are the four things which are there. Okay. So drying means if there is a moisture content in the fuel, that has to be released. Then pyrolysis, volatile release will occur. Then the char which is formed after volatile release has to be taken to a temperature where the surface oxygen can occur. Now, relative airflow direction controls the smoldering rate. If the air flows in this direction, then it will increase the smouldering rate. If it is in opposite direction, it may not.